Module 1, Lecture 6, Anatomy of the Cardiac Conduction System. In this lecture, we're going to identify the structure and course of all divisions and subdivisions of the cardiac conduction system. We're going to discuss the need for the atrioventricular septum and its role in causing synchronized contractions of the heart. Explain the role of the physiologic block of the atrioventricular node as a cardioprotective mechanism to prevent the transmission of very rapid atrial rates from reaching and depolarizing the ventricles. We're going to identify and describe how the heart's pacemaker control, rate, and rhythm are determined, and locate and label each structure of the cardiac conductive system. So the cardiac conductive system starts with the SA node and goes through the atria, through the AV node, and then down through the ventricles. If the heart was just composed of muscle tissue, the electrical impulse would travel unimpeded from the atria to the ventricles, causing simultaneous contraction of the atria and the ventricles. And so for this case, we have the electrical conduction system to prevent that, and the AV septum, the atrioventricular septum. So the atrioventricular septum, which is shown right here, represents a non-conductive wall between the atria and the ventricles. So essentially, it takes all the conduction that starts at the SA node and goes out across the atria and then wrangles it back so it will only go through the AV node here. The AV node only represents communication between the atria and the ventricles. Its function as the gatekeeper for the electrical impulse is very important. You do have conditions that we'll talk about later that actually will bypass the AV node and actually have extra conduction routes that are on the other side of the AV node, but that's not what we're talking about here. We're talking about just an electrical physiologic block that is in the normal heart. You've got your pacemaker cells and your conductor cells in the electrical conduction system. Now, these are going to be cells that are not necessarily designed to expand and contract like your myocardial cells are, but these are going to be specialized to transmit the electrical impulse in an organized manner. You've got pacemaker function, with the SA node being your primary pacemaker, but your pacemaker dictates the rate at which the heart will circulate blood. It creates organized beating of all cardiac rhythms and sets the pace for the rhythm. The SA node is not the only pacemaker, but it is the primary. So I've mentioned in earlier lectures that the body likes its numbers. The heart rate likes to be between 60 and 100. The SA node is what sets that pace. Now, of course, there's other things that affect that, like parasympathetic response and things like that could slow it, or sympathetic response that could speed it up. But the SA node in its normal setting should pace the heart at around 60 to 100 beats per minute. So the SA node is located in the upper posterior portion of the right atrial wall of the heart, and it is the site of the initial impulse formation in a healthy heart. The primary pacemaker of the heart, and it fires at 60 to 100 beats per minute. So your internodal pathways, you note here, are actually conduction lines that go through both the right and the left atria. The atria have to conduct in synctium, or at the same time, and so when that impulse is formed and released, it has to have a way to go through the atria so both the right and the left side can contract. So the internodal pathways actually transmit the impulse across the atria, and then they meet back at the AV node. The AV node is located on the floor of the right atrium above the tricuspid valve. So at the AV node, you actually have an electrical delay of about 0.05 seconds. This allows for a complete filling of the ventricles. So remember in past lecture when we talked about the atrial kick, this allows for the atrial kick to allow that last 10 to 40% of blood that didn't flow just by gravity into the ventricles to get squeezed into the ventricles before it moves the impulse forward. It should be the only pathway of atrial electrical impulses to the ventricle. So the AV junction, not the AV node, is going to be just below the AV node. The SA node joins the bundle of His by the way of the AV junction. If the SA node fails or slows below the normal rate, AV junctional tissue will initiate electrical activity, and thus the role of the secondary pacemaker. So as the secondary pacemaker, the rate would be somewhere in the neighborhood of 40 to 60 beats per minute. So just as I was mentioning earlier, sometimes in some hearts, they may have what's called an accessory pathway or an irregular muscle connection between the atria and the ventricles that bypass the AV node. That can lead to future issues for that person. The bundle of His just below the AV node and the AV junction lies at the top of the interventricular septum. It's referred to as the common bundle, and at the bundle of His, just like with the AV node, it should have an intrinsic firing rate, if it has to pace, at 40 to 60 beats per minute. The tissue in the bundle of His and the tissue surrounding that area actually receives blood from the left anterior and posterior ascending coronary arteries, and this is going to be at the septal connection between the upper and lower chambers of the heart. Then the bundle of His divides into two main bundle branches. So you've got the right bundle branch and the left bundle branch. The right bundle branch will go to the right ventricle, and the left goes to the left ventricle. So the left bundle branch begins at the end of the His bundle and travels through the interventricular septum and ends at the beginning of the left anterior fascicle and the left posterior fascicle. And the right bundle branch innervates the right ventricle and right face of the interventricular septum, and it terminates in the Purkinje fibers associated with it. Then you have the Purkinje network. The Purkinje network is going to be fibers that spread throughout the ventricles. The Purkinje network is what is actually going to pick up as a third line pacemaker in the ventricles. And if the Purkinje network, all these fibers that surround the ventricles of the heart, actually have to start pacing, then you're looking at a rate of around 20 to 40 beats per minute. So in review, the SA node should have a firing rate of 60 to 100 beats per minute. The internodal pathways that we mentioned earlier, they transfer the impulse from the SA node throughout the atria to the AV junction. The AV junction, the AV node, and the bundle branch slows the impulse at the AV node by 0.05 seconds to allow for ventricular filling, then sends the conduction on through to the ventricles. If the AV node has to, or the AV junction, the bundle branch, or the bundle of His has to start pacing, because maybe the SA node has quit working, then you're going to look at a rate of 40 to 60 beats per minute. The bundle of His then bifurcates into the bundle branches. You've got your two main bundle branches, the left and the right, that transmit impulse to the ventricles. The left bundle branch actually then branches off into your fascicles. The right branches off into your Purkinje network. The fascicles on the left side then branch off into the Purkinje network, which spreads the impulse throughout the ventricles, essentially wrapping the ventricle. And it could serve as a third line pacemaker. And if it has to serve as a third line pacemaker, then your heart rate would be in the 20 to 40 beats per minute. And you don't want the ventricles to have to pace the heart. So this is just a graphic of what happens when you have the electrical impulse starting at the SA node. So when the SA node depolarizes, the conduction travels through the internodal pathways and it moves rapidly through the AV node. Now remember, you've got your AV septum here that prevents any of this conduction from going, and it routes it all back to the AV node. The AV node, after the atria has depolarized, will hold up the conduction for about 0.05 seconds to allow for ventricular filling. Then it releases and it goes through the bundle of His into the left and right bundle branches that then transmit the impulse to the Purkinje network, and then you have a complete transmission of electrical conduction. And this concludes Lecture 6. Please let me know if you have any questions.